Something left 3 I/Atlas. Not in the way science fiction has trained you to imagine, and not in a way that should frighten you. What actually happened is stranger, and in its own quiet way, far more astonishing. As this object, only the third confirmed visitor our solar system has ever received from interstellar space, curved around our sun and began its long retreat back into the dark between stars, it did something almost nobody was prepared for. It erupted. Gas and chemistry poured out of it in combinations and quantities that no instrument pointed at a passing object had ever recorded before. And what came out wasn't simply water and dust drifting into the void. It was something closer to a diary, a frozen chemical record sealed in molecules and isotopes, written billions of years before Earth existed. It came from a star system so old it has almost certainly already died, from a region of the galaxy so distant and so cold that nothing from that environment has ever come this close to us before. And on June 22, 2026, a paper published in the journal Nature, built from data gathered by the James Webb Space Telescope, told us exactly what was written inside that diary. The answer caught the researchers off guard. It surprised the astronomers who had been tracking 3 I/Atlas since the week it was first spotted, and it has quietly reshaped what scientists understand about the conditions under which comets and maybe planets can form elsewhere in our galaxy. If you want to know what came pouring out of this interstellar traveler, what it tells us, and why a comet passing briefly through our solar system just handed us the clearest chemical portrait we've ever had of a world we will never visit, stay with me, because this is one of the most remarkable stories in modern planetary science. Let's go back to where it began, because the story of 3 I/Atlas is really the story of how fast the world's astronomers can move when something unexpected shows up. On July 1st, 2025, the Atlas Survey Telescope in Rio Hurtado, Chile, the Asteroid Terrestrial Impact Last Alert System, a NASA-funded network built primarily to watch for objects that might threaten Earth, picked up a faint moving point of light. The detection was automatic, but within hours, astronomers around the world had it up on their own instruments, checking and rechecking the numbers. What they found made the orbit unmistakable almost immediately. This object wasn't following the kind of path anything born in our solar system follows. Its trajectory was hyperbolic, the signature of something moving too fast to ever be captured by our sun's gravity. It hadn't formed here. It was simply passing through, on a one-way trip that started somewhere else entirely. It became only the third interstellar object ever confirmed, after Oumuamua in 2017 and Borisov in 2019. It was given the designation 3 I/Atlas, the 3 for third, the I for interstellar. And within days, essentially every major telescope on Earth, along with several spacecraft already stationed elsewhere in the solar system, had been redirected to study it. What set this object apart from its two predecessors was immediately obvious: activity. Oumuamua had been strange and hard to classify, but it showed none of the clear signs of a traditional comet, no obvious gas emissions, no glowing envelope of material around it. Borisov, by contrast, behaved almost exactly like a familiar comet from our own solar neighborhood. 3 I/Atlas did something in between and then went further. Just one day after its official discovery, on July 2, 2025, astronomers David Jewett and Jane Liu used the Nordic Optical Telescope and confirmed the object was clearly active, wrapped in a diffuse, spreading cloud of material actively being ejected from its surface. It had a coma. It had a tail. Multiple observatories confirmed this almost in unison. The comet had a reddish hue, similar to what's seen in D-type asteroids and in Borisov itself, a color caused by organic compounds on the surface that have absorbed radiation for enormous stretches of time. And it wasn't leaking material quietly. At the time of discovery, it was already shedding roughly 6 kilograms of fine dust per second and 60 kilograms of larger particles per second. This was not a silent, inert rock drifting past us. This was an active, outgassing visitor, and it was going to have a great deal to tell us. What followed was a cascade of encounters that turned into one of the most coordinated observational efforts in the history of astronomy. In early October 2025, the comet swept past Mars at a distance of about 29 million kilometers. The Mars Reconnaissance Orbiter caught it, the MAVEN spacecraft imaged it, and the Perseverance rover, which had spent years methodically searching the Martian surface for signs of ancient microbial life, paused its work and turned its Mastcam instrument skyward, photographing a comet from another star system as it drifted past a neighboring planet. Take a moment with that image, a robot built to search for the origins of life on Mars, photographing a messenger from a star system that may have died before our sun was even born. In October, 3 I/Atlas reached perihelion, its closest approach to the sun, passing inside the orbit of Mercury before swinging back outward. It passed Venus in early November, then swept by Earth in late December at a closest distance of about 270 million kilometers. Never a danger to us, but close enough in astronomical terms to matter. And by then, nearly every capable instrument in the solar system had been pointed its way. NASA's Parker Solar Probe captured roughly 10 images of the comet every day for 18 consecutive days as it passed. The Europa Clipper, en route to study Jupiter's icy moon Europa, was reprogrammed mid-flight to devote 8 hours of continuous imaging to the comet. On November 6th, the Psyche spacecraft, itself on its way to study a strange metal-rich asteroid, interrupted its own mission for 8 hours to turn its cameras toward 3I/Atlas. The test satellite, normally scanning the sky for planets orbiting distant stars, captured 28 hours of observations in mid-January 2026. More than a dozen separate NASA missions contributed data, joined by ESA's JUICE mission, the Jupiter Icy Moons Explorer, and the ExoMars Trace Gas Orbiter. By the time 3I/Atlas passed Jupiter in March 2026, coming within about 53 million kilometers of the planet before being gently nudged onto a slightly altered path by its gravity, nearly 500 scientific papers had already been written about this single object. But the most dramatic chapter of the whole encounter happened in late December 2025, as the comet made its closest approach to Earth. NASA's SPHEREx mission, observing in infrared, caught the comet doing something researchers would later describe simply as erupting, not in a destructive sense, but in the sense of a sudden, violent release of material from deep within its interior. In a short span of time, water emissions spiked 40-fold. To understand why that happened, it helps to understand what a comet actually is on the inside. Comets are roughly 1/3 water ice, but that ice sits buried deep within the nucleus, insulated from the sun's radiation by layers of material above it. Think of it the way you'd think of a frozen dessert with a thick shell on the outside. The surface can be warming for a long time before the heat ever reaches the frozen core underneath. It wasn't until roughly 2 months after 3I/Atlas had already passed its closest point to the sun, as it was pulling away again, that the sun's accumulated heat finally worked its way down to the buried ice and triggered a sudden, dramatic release. And what came out wasn't only water. Mixed into that vapor were methane, methanol, ethane, formaldehyde, and other carbon-based molecules, a chemical catalog that had been locked inside this object since before our solar system existed. That eruption also produced another first. Comets in our own solar system generate X-rays through a process called charge exchange, in which gas streaming off the comet interacts with the constant outward flow of particles from the sun. But every previous attempt to detect X-rays from an interstellar object had come up empty. Nothing from Oumuamua, nothing from Borisov. When Japan's XRISM satellite picked up a faint X-ray signature from 3I/Atlas in late November 2025, it marked the first time this had ever been observed from something that originated outside our solar system. At the time of detection, the gas cloud surrounding the nucleus stretched out to roughly 400,000 kilometers, wider than the average distance between Earth and the Moon, large enough that all 8 planets of our solar system could theoretically be lined up inside it. The detection confirmed that interstellar comets interact with the sun's solar wind in essentially the same way comets born in our own system do, and it gave astronomers a new technique for studying whatever interstellar visitor comes next. The comet's own rotation told researchers something else entirely, a direct physical record of how violently the outgassing was reshaping it. Before its close pass by the sun, 3I/Atlas completed one full rotation roughly every 16.2 hours. By December 2025, that had dropped to just 7.1 hours. The object was spinning more than twice as fast as before. The cause was the jets themselves. As gas and dust blasted outward from specific points on the nucleus, the escaping material acted like small rocket thrusters, pushing against the comet's spin and gradually winding it up. Astronomers tracked this by watching the comet's brightness fluctuate as its active jets rotated toward and away from Earth, using those variations to measure the spin with increasing precision. Then, on January 22, 2026, something close to a cosmic coincidence gave scientists their sharpest measurement yet. On that date, 3I/Atlas aligned almost perfectly along the line connecting Earth and the Sun, within 0.69 degrees of exact alignment. With the Sun positioned directly behind it from our point of view, the shadows normally cast by the comet's dust particles vanished, and scattered light combined constructively, producing a sudden 20% surge in brightness. That surge let the Hubble Space Telescope isolate the comet's solid nucleus from the glowing cloud of gas surrounding it, yielding a measured nucleus radius of approximately 1.3 kilometers, smaller than some earlier upper estimates, but squarely within the normal range for active comets in our own solar system. Not a monster, not a city-sized object, an ordinary-sized comet carrying extraordinary chemistry. That same period of clarity let researchers map the comet's surface in more detail than had previously been possible. By filtering out the uniform glow of the surrounding coma, scientists identified 4 distinct jets erupting from the nucleus. One larger jet pointed toward the sun that had already been observed earlier, now aimed toward Earth, and 3 smaller jets spaced roughly 120 degrees apart from one another. That near-perfect symmetry caught people's attention immediately, and online speculation followed quickly. The idea that such a regular geometric pattern couldn't have arisen by accident, that it implied something built rather than something natural. Planetary scientists were quick to point out that regular patterns like this can, and do, emerge naturally from the interaction between a comet's rotation, its internal structure, and the way volatile ices are distributed just beneath its surface. Specific pockets of ice heating and venting in a rhythm set by the comet's own spin can produce jets at very regular angular intervals. It looks deliberate. It isn't. And for what it's worth, the SETI Institute and Breakthrough Listen ran their own search for radio signals from 3I/Atlas using the Allen Telescope Array. They found nothing. No technosignatures, no signals of any kind, just chemistry, which brings us to what the James Webb Space Telescope found, the observation that produced the most detailed and most revealing analysis of 3I/Atlas to date, published in that June 22, 2026 paper in Nature. A team led by Martin Cordner of NASA's Goddard Space Flight Center interrupted Webb's scheduled observing time to point its near-infrared spectrograph, NIR-SPEC, at the comet as it began its retreat from the inner solar system. NIR-SPEC works by analyzing the specific wavelengths of light that different molecules absorb and emit, essentially reading each chemical's unique spectral fingerprint. What it found in 3I/Atlas was startling. The ratio of methane to water was roughly 11 times higher than in any solar system object ever measured. 11 times. No comet from our own system, however unusual its chemistry, comes anywhere close to that number. Even more revealing was what the data showed about deuterium, SO, a heavier form of hydrogen. Ordinary hydrogen has a single proton in its nucleus. Deuterium carries a proton and a neutron together. Water molecules can incorporate either form, and the ratio between deuterium and ordinary hydrogen in a comet's ice acts as a kind of thermometer, preserving a record of the temperature conditions in the environment where that ice originally formed. Colder environments produce proportionally more deuterium. The extremely cold, distant fringes of a planetary system far from any star's warmth produce far more deuterium than the warmer, sunlit regions closer in. In 3I/Atlas, the deuterium to hydrogen ratio came out roughly 30 times higher than in comets from our own solar system, and about 40 times higher than in Earth's oceans. These aren't small deviations. They point to a formation environment so cold, so far removed from any star's warmth, that nothing in our own solar system ever formed under comparable conditions. A separate study from researchers at the University of Michigan, published in May 2026, independently confirmed the figure, the highest deuterium ratio ever measured in any solar system object, borrowed or otherwise. As researcher Teresa Pankeo put it, this is proof that the conditions that produced our solar system are not universal across the galaxy. It might sound like an obvious statement on its face, but it needed direct evidence to confirm it, and now it has that evidence. Taken together with carbon isotope measurements used to estimate the comet's age, the extreme deuterium ratio points to something remarkable. 3I/Atlas appears to have formed in the frigid outer reaches of a planetary system that existed somewhere between 10 and 12 billion years ago. 12 billion years ago, the universe itself was less than 2 billion years old. Our sun didn't exist yet. It wouldn't begin forming for another roughly 7 billion years. Whatever star produced this comet came into being during what astronomers call cosmic noon, the peak era of star formation, when new stars were being born across the galaxy at a far higher rate than they are today. That star is almost certainly gone now. It lived out its stellar life, went through its own evolution, and burned out or exploded billions of years before anything living existed on Earth. The comet it left behind was flung out into the space between stars, and it has been traveling ever since, for billions of years, across a staggering distance. Calculations tracing its trajectory back roughly 10 million years show it passing near 62 other stellar systems along the way, though none of those encounters came close enough to meaningfully alter its course. It just kept moving, drifting through the emptiness between stars until it finally reached us, and our sun's gravity pulled it into the close encounter that, at long last, unlocked the chemistry that had been sealed inside it since the universe was barely out of its infancy. A complementary study using the Very Large Telescope in Chile, led by Cyrielle Apetom of the University of Edinburgh, analyzed the comet's carbon and nitrogen chemistry through cyanide, a simple molecule made of one carbon atom bonded to one nitrogen atom. The ratio between different carbon isotopes in that cyanide added further weight to the picture drawn by the deuterium data. The carbon-13 to carbon-12 ratio in 3I/Atlas's cyanide differed from what we see in solar system comets in a way that's consistent with formation in an extremely old, extremely cold environment. Every independent line of chemical evidence is pointing the same direction. This object came from somewhere very old, very cold, and very far from anything we know. Researcher Stephanie Milam of NASA Goddard, a co-author on the Webb paper, put the discovery's significance in its broadest possible context. For us as scientists, she said, finding these rare isotopes is fascinating, but the bigger picture here is looking at the possibilities of prebiotic chemistry elsewhere in the galaxy. Prebiotic chemistry refers to the molecules that, under the right conditions, can combine and interact to form the basic building blocks of life. 3. I/Atlas carried methanol, formaldehyde, and other carbon-bearing organic compounds in its ICE, the kinds of molecules astrochemists consider directly relevant to the chemical origins of biology. To be clear, the comet did not carry life, and nothing about this discovery suggests that it did, but it carried the raw ingredients that, on a world with liquid water and a source of energy, could become the starting material for life to eventually take hold. And it carried those ingredients from a star system that existed 10 to 12 billion years ago, in a region of the galaxy so ancient and so cold that the stars forming there today bear little resemblance to our Sun. The fact that the same basic chemical ingredients seem to show up across that much of cosmic history in that much variation of stellar environment is genuinely significant. It suggests that the chemistry needed to begin building toward life isn't some rare accident unique to our solar system. It may be far more widely distributed across the galaxy than we've previously had any direct evidence to confirm. On March 16, 2026, 3I/Atlas passed Jupiter at a distance of about 53 million kilometers, close enough for Jupiter's gravity to leave a small but measurable mark on its trajectory, a shift of only a few meters per second in velocity. In the scale of ordinary human experience, that's nothing. But across the almost incomprehensible span of an interstellar journey measured in billions of years, even that small nudge reshapes the path ahead. It's likely the most significant gravitational encounter 3I/Atlas has experienced since it left its home star system, and it's the last meaningful one it will ever experience from any star again. Past Jupiter, the comet continues outward, decelerating slightly under the Sun's remaining gravitational pull as it climbs away from the inner solar system, before eventually accelerating again as it escapes entirely, heading back out into interstellar space for good. The instruments that could track it are, one by one, losing sight of it, but the data they gathered isn't going anywhere. Astronomers now estimate that hundreds of interstellar objects are likely passing through our solar system at any given moment. We've simply lacked the detection capability to find most of them. With the Vera C. Rubin Observatory's legacy survey of space and time now running in full operation, researchers expect a new interstellar object to be spotted roughly once every 1 to 2 years going forward. The sheer volume of work already produced around 3I/Atlas, nearly 500 papers, data gathered from more than a dozen spacecraft and missions, observations from some of the most powerful telescopes ever built, means this single comet will remain a reference point for understanding interstellar visitors for decades to come. Whatever comes next, 4I, 5I, objects that don't have names yet because they haven't been found, will be interpreted, at least in part, through what 3I/Atlas revealed. What came out of 3I/Atlas, when the Sun's heat finally reached down into its buried core and released chemistry that had been locked away for 10 billion years, was something close to a message from the ancient universe. Not a signal in the way we usually imagine one, no transmission, no deliberate broadcast, but a chemical message, written in isotopes and molecules that our instruments were finally able to read. And the message it carried is this: the raw material for building worlds, for building comets, for building the compounds that chemistry needs to begin its long, uncertain path toward complexity, and maybe eventually toward life, already existed in our galaxy when the universe was barely 2 billion years old. It existed in cold, dark, distant places our sun never touched. It survived for 10 billion years in frozen silence, drifting between stars, until it finally arrived here and briefly lit up the instruments of a civilization that had no idea it was coming. If stories like this fascinate you, the idea that a single object passing through our sky can carry evidence from a time before our sun even existed, this is exactly the kind of real, evidence-based science this channel is built around. If you'd like more of it, subscribe and turn on notifications, because the next interstellar visitor is already out there somewhere, and when it arrives, we'll be ready for it.